Welcome to lecture 33. We have been discussing for the last 2-3 lectures how to estimate or determine the stability of slopes, and we were looking at the simple method of slices. Let us just review the same. The method of slices is a very simple approach. We are not worried about the geometry of the material or the slope. What we do is we pick up a center O, draw an arc of a circle, and then we assume that this soil mass A, B, C, maybe D, this is likely to slide. You realize that this is a very irregular shape, so what we try to do is divide this into number of slices, and you will realize each slice is almost like a rectangle. Usually if you are around 10 to 15 number, the accuracy is good enough. Then what we look at is the equilibrium of each slice. So if this is 1, 2, let's say you look at the slice 4, and when you divide it, you can make sure that the width is about the same. And let's look at the center where you can draw the tangent to the radius, and let us say this angle is alpha I, so which means it will be alpha 4, where alpha I is the angle with respect to the vertical. So now you can find out that what will be the average height. So the weight is equal to the fourth slice, gamma into hi into b, and of course 1 perpendicular board. If it is a saturated soil, you take it. Otherwise, generally, let's say slopes are rarely saturated, we say gamma total. We'll come back to another situation where if the water table is high, you will have gamma total here and gamma saturated below. And if I now look at the equilibrium of forces, this is W4, you can say this will be the normal force, and the tangential component is the one that is trying to cause sliding, and we need to find out the shear resistance. So what we try to do is find out this angle again with respect to the radius is alpha 4. So you will find that the shear stress causing sliding is W4 sine alpha 4, where alpha 4 is this angle with respect to the vertical. Of course, the normal component would be N4 is W4 cos alpha 4. In order to make it easy, just say I, where I can go from 1 to N. And then once you have the normal force, and the slice has a tendency to rotate or move to the right and down, the shear resistance is mobilized here, which will be equal to cohesion into this length. And that length would be equal to, if this is B, you agree that it will be B secant, I call it as L4, C B secant alpha 4, plus the normal component is given as W4 cos alpha 4 into tan. The strength properties are given as C and phi. Then when you have these are determined from the Moore envelope, sometimes what we do is, this is sigma and tau, intercept is here, this is phi. We say for design CD is equal to C by factor of safety. Similarly, tan phi d is equal to tan phi by factor of safety. So these are the mobilized or design values. We are already putting in the factor of safety, so that then you can work out under the mobilized condition. Maybe Fs can be 1.5, 1.3, whatever it is. And then similarly, Fs with respect to C, Fs with respect to phi. And often you can say, you can take them to be same. And then we can use them for our analysis too. So here what you will find is the strength mobilized is equal to C cohesion, or if you want to put, you can put C design or C mobilize, B secant alpha plus the normal component, which is equal to Wi cos I into tan phi. And you agree that this force is tangential to the circle, so it will be perpendicular to the radius. So the radial distance is r, and then the centroid of the slice will be at a distance xi, and you also know, very easy to find out, xi is nothing but r sine alpha I. This is the radius, this angle is alpha, so I can say this angle, sorry, I think it should be, yeah. So this distance is r radius times sine alpha I. Now you can calculate the overall factor of safety by taking moments of all the resisting forces about the center O and divide by the moment of the activating forces. By definition, moment of resisting forces, moment of activating forces. And then we sum it up for slices 1 to n. So you write it as sigma I going 1 to n. This should be equal to Cb sine secant alpha I plus Wi cos alpha I tan phi. Let me write mobilize just to make sure that you also appreciate you can take a factor of safety from the maximum value to the allowable value, divided by, again, sigma 1 to n. The activating force is Wi sine alpha I. So using a simple graph paper, you can plot these slopes, slices, and do, or if you are using a Excel sheet, a worksheet, you can simply say Microsoft Excel. You can easily program it on your computer laptop, and you will determine this factor of safety for a given circle. Then you have to search around for the minimum by taking different centers and different radii. Suppose I take this center, I can take another, a third with the same center, different circles, or pick up different centers and draw them. So over this region, look for different centers and different radii, and then contour it so that you get minimum factor of safety. That's how we determine the least value is the factor of safety for a given slope. What is interesting is this is a very simple mechanics problem. All that you need to know is the weight of the slice. Now this was used to be done till about 1950s and 60s. Then somewhere around that time, Bishop at Imperial College looked at the problem a little more in detail and then looked at the forces acting on the sides of the slides. We never looked at the interaction between the slides. So what we say is that same method, there are two here. There is a more rigorous method, another is a simplified one. Let us only look at the more easy one. If you are more interested at a course, you can go for rigorous method of analysis. The approach is exactly the same. Say this is the ith slice. So this will be Wi. What we will now do is look at the various forces on the slice. What we now consider are the interslice forces. These are called, as you can see, this slice is trying to go down and go to the right. So the activating forces on the slice, each one is independent, but it's interacting with the adjacent ones. So the force on the left side, we can say the normal force is called EI and the tangential force is TI. And because this slice is trying to move to the right, the slice on the right will try to give opposite forces, TI plus 1 and EI plus 1. And then rest of the forces are exactly the same as before. As you can see, the normal force Ni and the shear force Si. You can say, maybe in order to simplify that, delta T is equal to Ti minus Ti plus 1, and delta E is equal to Ei minus Ei plus 1. This is the net force which is being added to the forces on the ith slide. So what you are now trying to do is, earlier we neglected these forces and simply we satisfied equilibrium. Now we need to worry about how these forces can be included in our analysis. So let us say what will be the forces downward and what will be the forces upward, so that I would like to calculate Ni including these forces. So in order to do that, let us say we resolve all the forces in the vertical direction. I would like to include the components that are going to contribute to the vertical direction. So if I do that now, here anyway, before that, let me write the shear strength mobilized on the bottom slice is equal to C by factor of safety into, shall I call this as delta Li, plus the normal stress or normal force Ni tan phi by factor of safety. Okay, so this is the mobilized tension. C and phi are obtained from our Moore envelope. I'm saying a part of it is allowed or mobilized, and we assume a certain factor of safety, maybe 1.5, 1.7, and try to get SI, because please remember, now we are satisfying equilibrium equation. So the forces should be in equilibrium in order to calculate the resulting forces. So in order to do that, you need to assume a factor of safety of the strength parameters. So if I resolve now, the downward forces are, you can see Wi, which is acting downward, Ti minus Ti plus 1, which is what we call as delta T. So downward forces are Wi plus delta T. Maybe if you want to make it, let's make it I. And what will be, they should be equal to, some of the downward forces should be equal to some of the upward forces. And again, if this angle is alpha I, and this obviously will be alpha I, so it will be equal to Ni cos alpha I. Ni cos alpha I, that will be the vertical component. Similarly, Si sin alpha I are the vertical forces. Please remember, it's a very simple equilibrium equation. Some of the downward forces should be equal to some of the upward forces, and that will satisfy Newton's law that net force in the vertical direction is 0. If you do that now, let's substitute for Si, which is interesting. That is where the uniqueness comes of Bishop's method. Si we have written as C by Fs into delta I. Delta L is the length of the arc or the segment that you say A to B. So this should be equal to C by factor of safety delta Li plus Ni and phi by factor of safety into sin alpha. If the width of the slice is B here, can I say delta Li is nothing but B secant I? So we can put that in here. Okay. Now what you find interesting is you have Ni here, another term Ni. If I want to simplify this, so what we will write it as Wi plus delta Ti minus, you have C by Fs delta Li into sin alpha I is equal to Ni cos I plus the term here. So you will have Ni cos alpha I plus Ni tan phi sin alpha I by factor. Or you can take Ni out, it will be equal to cos alpha I plus tan phi by factor of safety into sine alpha I. And you can substitute if you want delta Li is equal to B secant I. So it doesn't matter, it's just a simple substitution. You can calculate separately or substitute that. Now you find this force Ni is a function of Wi, Ti, and even the strength mobilized. That is how we get the iterative or the uniqueness of this approach. So now we can solve for Ni is equal to Wi plus delta Ti minus C factor of safety into delta Li sine alpha I divided by cos alpha I plus tan phi by factor of safety into tan into sine alpha I. So you know how to calculate Ni, and once you know Ni, we go back to this equation, get Si. Si is equal to C delta Li by factor of safety plus Ni tan. That's how we wrote the strength mobilized. So we know how to, here there is another factor of safety. This is how you determine the normal component. So what I'd like you to note here is when I write this equation, you are also including the strength mobilized, because when you are resolving it to the vertical direction, not only the weight, downward forces, plus the shear strength mobilized also has component. So once you know the strength mobilized, we write the same equilibrium equation as before, which means sigma I going from 1 to n Wi r sine alpha I should be equal to sigma Si into r I going from 1 to n. And you can say that from here, because Si is written, so the factor of safety would be as before sigma I going from 1 to n, that is summing up all the terms, and we try to simplify here, and that is how we'll write that. C into Bi plus Wi tan phi plus delta T tan phi prime. Where did we get that? Ni tan phi, so delta T tan phi prime, and here is the additional term that we will get divided by its m alpha I. This is a new term that you get when I substitute and simplify the term. Sigma I going from 1 to n cos alpha I plus tan alpha I tan phi sine alpha I factor safety. And here in the simple version we neglect the effect of the vertical interslice forces. So finally we will get, I think I should have put Wi here. So what we will do now is simplified Bishop's method. The factor of safety is equal to sigma I going from 1 to n C Bi Wi tan phi prime by m alpha I divided by Wi sine alpha I going from 1 to n. The radius r gets cancelled because we have r sine I and you have r. The main change is in the term m alpha I is equal to cos alpha I plus tan phi prime by factor of safety into sine alpha I. This is a new term, so that earlier we did not have it in the expression. If I neglect the forces Ei and Ei plus 1, then this term becomes equal to 1 and we get the same expression as for method of slices, simple ordinary method of slices. By considering the normal forces and neglecting the vertical interslice forces along the sides of the interslice force, Bishop has introduced this factor. Now the interesting thing is you are calculating factor of safety with this expression And on the right side, you will see that this term has a factor of safety. So it becomes an iterative method, which means you got to assume for each trial circle factor of safety. I assume a value, put that in to calculate m alpha I. For each slice, I have to find out how much is m alpha I, knowing cos alpha I and sin alpha. And once you know that, I go into this equation, calculate the factor of safety. If this factor of safety is equal to assumed one, then you say your result is good. Otherwise, what we do is go iteratively, assume Fs. Let's say I call it 1, calculate Fs, and I call it as Fs2. If Fs2 is equal to Fs1, you have done a very good job of estimating, then the solution is correct. If Fs2 is not equal to Fs1, then redo the calculations and estimate Fs3. Again, compare Fs3 with Fs2 now. If they are equal, the solution has converged. Otherwise, again go back with Fs3, go back. Usually it takes about 4 to maybe 3 to 5 iterations. 3 to 5 iterations. Let's say I start with 2, I may get 1.8, I substitute 1.8, I get 1.7, then I get 1.65. And then maybe if I substitute 1.65, I'll get very close to that. Basically, you can put in a kind of convergence criteria that the difference between the two, if it is less than 1%, that's good enough. So Fs new minus Fs old divided by Fs new, if it is less than, say, not 1. That means it's 1% less, then you got the convergence. So for the assumed trial circle, we now calculate the factor of safety based on Bishop's method. And the whole crux of the approach is the consideration of the normal forces on the two slides, because of which the amount of force developed will be different for the shear resistance. And that will also contribute to additional factor of safety, and then you'll get one factor of safety. The rest of the method is exactly same as what you have done before, which means you search for the minimum in the space as before. So in this region, take number of centers, draw different circles, different radii, get factor of safety. Please remember, for each trial circle, you have to go through this iterative method. And if once you do that, you will get some minimum factor of safety. And that will be the more correct one, factor of safety minimum from Bishop's simplified method. And if you compare with the method of slices, generally factor of safety minimum from ordinary method of slices, the Bishop's method gives you a higher factor of safety. So what we find is, if I do based on ordinary method of slices, I get a lower factor of safety, which means you are very conservative. Whereas if I'm looking at the Bishop's method, I get slightly better. And this is required because otherwise you'll be wasting a lot of money in trying to make the slope flatter. Suppose with the ordinary method of slices, the factor of safety is 1. This will give you 1.4 or say 1.35. And you say, this is much better, so I don't need to worry about possible failure because this is too low. So nowadays, nobody uses the ordinary method of slices. We have gone through this derivation only to illustrate the method of approach, but really we go for Bishop's method or some of the more rigorous ones, like we have a Norwegian who has given a method called Jambus method. or another Britisher, Spencer, and the ultimate is called Morgenstern and Price method. The reason why we think these are better, because in the ordinary method of slices, no force equilibrium is satisfied. We just take the only vertical, resolve the forces in order to get the shear resistance mobilized. In the Bishop's method, Bishop's simplified method, normal interslice forces are considered, but the tangential interslice forces are not considered. Plus, we also consider vertical force equilibrium. So this is a good thing, and so you get a much more. Whereas these consider both vertical and normal interslice forces and equilibrium equations. But you will realize that the problem becomes statically indeterminate. So which means it's much more difficult to calculate, and we leave it to an advanced course to study that. But again, in the next lecture we'll see we go for mostly computer solutions, and we don't need to go into the equations. Computer methods using software which is readily available, and so it will be possible for us to calculate the factor of safety without going through all these equations. One more change I would like to mention, that in case there is water or seepage, how do we handle it? Both in the method of slices or Bishop's method, you have to account for water and the pore pressure. Let us say we have the slope here, and you are looking at the failure surface, and here is the typical slice, and let's say this is the phreatic surface. Now you agree that the soil below the water level, this is saturated. The soil is saturated. Here it will be total unit weight, which can be gamma total, let's say, less than or equal to saturated unit weight. We said that this height is HI. You divide this into HI1 and HI2. The height of the slice above the water table, the height of the slice below the water table. So the total weight Wi is equal to gamma total HI1 plus gamma saturated HI2 into, of course, B. You are taking the total unit weight above the water table and the saturated one below. Then when you look at the normal forces, Ni, you have to correct for the pore pressure, which is equal to Ui into Bi. So how do I get Ui? So if I put a piezometer here, I should find out this height, H, for the pore pressure, and so Ui is equal to gamma W into H pore pressure, wherever it is. So you have to account for the pore pressure. And once I find out the effective normal force, this is how we find out SI is equal to Ci into delta Li plus Ni minus Ui, this is the pore pressure, into Bi, of course, and tan phi by factor of safety. So you have the pore pressure coming into picture, and you account for it. That's how you take care of the water table or steady seepage. Then we'll next pass on to some of the particular cases where we have homogeneous soils or embankments on soft soil, or even same slopes under earthquake condition.